order to be able to hear the presenter in the room, but not have it picked up twice, we just need to use the directional mic. Simple. It's great. Good to learn.
Oh, sorry. 2 minutes, if I may.
This way. Keelan, you have to speak up a little bit.
Okay.
When you're talking.
Yeah.
Okay. Right. See you guys later. You're back online.
Apologies. There we go. Okay, so are we ready to sort of carry on then?
Yes.
Yeah. All right. So, okay. I think, given that we have an hour left, we should be able to actually go through all of this paper at the rate we've been going through the questions. So I think what we'll do now, if that sounds all right with you, is actually just go through the rest of them in order, now that we've had a look at the ones you had the most difficulty with and kind of got a sense of what we were doing. Does that seem all right?
Yeah.
Okay, so, and again, you know, we're still going to skip over the parts that are kind of pointless talking about, you know, define density. Well, either you can do it or you can't. That's not really something that I can help a great deal with. So question 1 in general, was this okay, mostly? Anything at all that stood out to you?
I think all right. Yeah. Yeah, one was all right. One was all right for us.
Yeah. Data. Yeah, so it's so one part is just putting some numbers into an equation, and then the second part is doing the uncertainties again. So yeah, I think that one was fairly all right. And indeed, we talked about the same thing with dealing with multiplying your uncertainties in the previous paper that we were looking at. So I think, to be honest, we'll actually skip over that one, despite what I said about going through all of it. So there's not much point talking about that. So, okay, actually, this one is worth talking about. How much? So, define electric field strength.
The force per unit of positive charge.
Yeah.
Yeah. Okay, so what does that actually mean? What actually is an electric field? That's trickier.
I'm unsure because I haven't really learned this that well. You explained it to me.
Okay, so an electric field is a way of thinking about all of the electrical forces that are acting. And one of the best ways of describing an electric field is it's the force on a test charge. So the electric field is if you imagine putting a charge in at a point, it's the force on that. However, it's important to note that the electric field isn't itself a force. So the electric field does not itself do anything. It's just a way of thinking about the electric forces from all of the various sources of electric force, which in this case is primarily charges. So yeah, that's something that's worth kind of understanding what we actually mean. So when we say the force per unit positive charge, what we're actually talking about is we're imagining taking a sort of a positive charge and putting it somewhere and then measuring the force on it. That's kind of what we mean when we talk about the electric field. Okay, so potential difference. We put charges on the two plates. Our electron comes in, it gains a velocity. Okay, this one is nice and simple. So, time taken, well, that's just speed equals velocity over time. Speed equals velocity. Oh no, distance. So time equals distance divided by velocity. Same difference. That bit's nice and simple. The magnitude of the electric field strength is a little bit more interesting. How did you go about doing that?
Do you want to explain it?
I'm not too sure. Yeah,
Okay, so we took the 2.5.
All right, if it's all right, Niels,
Yeah.
I would like Kieran to explain it, because
Yeah.
from what I have gathered, and please don't be offended by this, but I gather that Niels, you're more comfortable with pretty much all of this.
Yes.
Yeah. So, if it's all right, we're going to mostly focus on, when I'm asking questions, I'd like to mostly focus on getting Kieran. Is it Kieran? Sorry?
Keelan.
Right. Sorry. Right. If it's all right, I'd like to mostly focus on getting Keelan to answer these questions, because I think he's the one that actually needs to be trying to talk this through. Because talking your way through things is a very useful way to understand them.
I totally agree.
So, Keelan, how did you do this question, aside from ask Niels?
Is this for what, is it part 2 of the?
Part 2, yeah.
So, wait, trying to wait, okay, sorry. One second, I'm trying to look through my notes that I did. I think like so 2.5 kilovolts, and I put that into volts, which was 2,500 volts. Divided it, and I divided it by, I think it's, where's it before? Is it before centimeters?
Yeah. Okay, so this is the equation that you need for this question. E equals V over D.
Yeah.
This is essentially the definition of potential. And yeah, so there's not really much to this question. Ultimately, you are just plugging numbers into an equation. The thing I want you to kind of think about, and one of the points that I would like to make here, if it's all right, is you're going back and looking at your notes, and you're saying, oh, I divided this number by this number, and I'm not really sure what those numbers were. So what I would like to suggest for you in particular for things like this is always write down the equation in symbols that you are using before you put the numbers into it.
Okay, yeah.
Not because it is necessarily a super useful thing to do in terms of the actual point of doing it, but because if you write down the equation in symbols every time you're using it, you will get used to them much more easily and you will remember them much better than if all you're writing down is a series of numbers that don't mean much to you.
Yeah, okay, I get that.
All right. So I think in cases like this, that is a useful thing to try and do, because it will help you remember these things without having to try and sit down and learn them off by heart, which is a bit miserable.
Yeah, it's true.
So, part 3, show that our acceleration in the electric field is 1.1 times 10 to the 16 meters per second squared. So this one is F equals ma. All right, that's all this is. We have the force because we know the electric field. So in this case, force equals ma equals EQ. If I can try and make the writing we need. So we have force is the electric field times the charge. which is, what our electric field means. And then we also have F equals ma, which is just our standard Newton's second law. And so it's that acceleration that we're looking for. They gave you that one's slightly odd insofar as they've given you no sort of no room to do it really. It's just sort of, oh, we ran out of page, but never mind, it'll be fine. All right, use the acceleration given and your answer in part 1. What was our answer in part 1? It was the time. So this now we've moved on to Suvat.
Yeah.
So at this point, this is just Suvat. And really, the point to note with this one, I'm actually going to go back and draw on the diagram. Because y is a slightly odd one. What we're actually going to work out is we're going to work out this distance. We're going to work, and we'll call this z. Right? What we're actually going to work out from our Suvat equations is z. And then we're going to need to do the halfway minus z is going to be our y. That is by far the easier thing to work out. You can do it the other way around and essentially treat it as your electron falling to a certain height and get y straight away. But I think that's a little bit weird and overcomplicated. So I would recommend just doing it from rest as standard. And it's important to note that because Suvat is in one dimension, you can just treat your electron as being at rest at the start because it isn't moving up or down at all.
Yeah.
Okay, so explain why your calculation in 4 doesn't need to include the gravitational effects. Well, okay, why is that?
Sorry, can you repeat that?
Why don't we care about gravity in this case? Okay.
Wait.
Yeah. So what are we dealing with here? We're dealing with an electron. An electron is really, really tiny. It's also worth pointing out that when you came out with your acceleration, it's 1.1 times 10 to the power of 16. Right? That is 11 quadrillion meters per second squared. That's a really big number compared to, 10, which is what gravity is. So yeah, gravity is completely negligible here. Yeah. All right. Electron enters the field at time t equals 0. So this is our velocity time graphs. So in the x direction, it should just look like a straight line because nothing changes. And in the y direction, it should look just like a standard lineup. So they should look like that. All right, I think that one was mostly okay. Now 3 we've talked about. I'm running off the page here. So 3 we've talked about. So let's have a look at 4 now. So we've got 4, 5, and 6. We've got 45 minutes left. Okay, we're powering through this, but hopefully we won't end up with too much spare time. So what is meant by the frequency of a progressive wave? Oh, there's fancy terms, aren't there? So frequency of a progressive wave. This is actually a surprisingly high mark question for a definition. So first of all, what is a progressive wave? Either of you.
A progressive wave is the wave that is. I need to find the wording. I'm bad with words.
You can put it very simply.
What's it called? I know. I'm trying to. Progressive wave is the wave that. What? Ah, I'm cute. Nothing.
All right, I suspect that it would be useful for you to try and figure out what you mean here, so I'm going to give you a minute if that's okay.
Yeah. Actually, I cannot answer the question.
All right, so I would put it very simply.
Yeah.
In this case, at A level, and say simply meaning a progressive wave is fundamentally it's a wave that's going somewhere. All right. Now, that's a slightly odd term to use for a wave because fundamentally a wave is something where things aren't going anywhere, right?
Yeah.
You know, in a wave. But the important point is, in a wave, energy is traveling, but the medium is not. Right? That's the important point. So in a progressive wave, the energy is going somewhere. I think that at one point, Niels, you started to say it's not. And I suspect that you were going to say it's not a standing wave.
Yeah.
So in a standing wave, the energy is also not going anywhere, but it is in the wave. But yeah, so a progressive wave is fundamentally, it's a wave that is going somewhere. And when we say, oh, the wave is going somewhere, what we mean is that the energy associated with the wave is going somewhere. The wave fronts are traveling along. The frequency is the number of wave fronts that pass a given point per second. So the reason that it's asking for the frequency of a progressive wave is that this only makes sense if our wave fronts are in fact moving along. Right? For a standing wave, frequency means something else because it doesn't actually have these nice wave fronts that are just moving along and heading somewhere. But a progressive wave does. So it's nice and easy to define. Okay, then we go back to our cathode ray oscilloscope. I don't know why exam boards are still so obsessed with these things when they're ancient tech at this point. They really are. But yeah, so they love them, and we hate them, but there we go. So the trace produced on screen looks as above, and we have a time-based setting, and we want to find a frequency. So how would one go about doing this?
I'm not too sure about this question.
Okay, so this one is all about these kinds of really weird looking units by here. Right? Microseconds per centimeter is a unit that only makes sense in the case of an oscilloscope, really. Otherwise, it's just a very odd thing to consider, particularly given the prefixes. So what it means is your time-based setting is saying 1 centimeter on your screen is equivalent to 250 microseconds. Essentially, what it's doing is it's putting axes on your graph, right? So your oscilloscope is essentially, it's a graph, but with the axes not being labeled. And the time base and the amplitude base are a way of putting labels on the axes. So what you're saying is that this 1 centimeter gap by here, if I can make it, there we go, is equal to 250 microseconds. There we go. That's what it means. You can then further subdivide that and say, okay, so then in that case, one of these little squares is going to be how long? 50 microseconds. And at that point, you can say, okay, well, how do I figure out a frequency? And we go back all the way to our, okay, f equals 1 over t. And if we want the time period, we're going from here to here. And we measure that using our time base, where we've converted one little square into 50 microseconds.
Yep.
Okay. Make some sense? Not make some sense? Where are we at?
Yeah, it makes sense.
Cool. Okay. So the loudspeaker. Yeah, I apologize. I come from a background of one-to-one tutoring rather than teaching, so I tend to. I suspect I probably err more towards, over interaction than some of your other tutors. But yeah, that's just me, I'm afraid, and you're stuck with it. So the loudspeaker in B emits the sound in all directions. A person emits the loudspeaker, attaches the loudspeaker to a string and swings it around. That's why, but fair enough, if they really want to. Maximum frequency. Okay, so now we are at our Doppler effect. The Doppler effect, so this is one where I can't tell you much about the maths behind it, beyond, there is an equation, which you can see in your mark schemes. It's F naught equals, what have they got? F S V. Okay. That's our Doppler shift equation as it's given to you in your specification. So you know the frequency of the source, you know the frequency of that you're hearing, the FO. So you're just looking for a VS, your velocity of the source. There is not a great deal more to it than that, I think. Okay. Yeah, so there's not a great deal more to say about the maths behind it. However, there is a great deal to say whenever we start to explain things qualitatively. So, the variation in the frequency of the sound heard by the observer. So the Doppler shift is quite a nice one to sink your teeth into qualitatively, because it's got quite a nice feel to it. So, where are we going to start? Keelan, why don't you have a go at explaining to me why we are going to get a higher frequency when something is moving towards us?
When it's moving towards us, aren't the waves more no.
Yeah, say what you were going to say.
Aren't like the waves more compressed?
Yeah.
They're like, close together, so it's high pitch.
Yeah. So essentially, what you're getting happening is if your source, so you have your source, which is a box in this case, and it's giving out a wave. It's a very pretty wave, I know, but it'll have to do. If your source is moving towards you, it's going to compress your wave. It's going to make your time period shorter and your frequency higher. If it's moving away from you, it's going to kind of stretch out your wave, and it's going to make your frequency lower. All they will, so that's the kind of, I think, obviously that's not a sort of super mathematical scientific explanation of the effect, right? squishing and stretching a wave doesn't really make a lot of sense if you start to think too deeply on it. But it is a very good way of, if nothing else, remembering which way around the Doppler shift works and all the rest of it.
Yeah.
So in this case, the variation in the frequency, actually what they were looking for was when the loudspeaker is moving towards you, you get a higher frequency. When it's moving away, you get a lower frequency. That was all they were after here. So this was an example of where you just needed to state the obvious, really, for the question.
Okay.
So yes, I would argue that describe and explain is perhaps being a little generous to itself. It's more, describe. But yeah, so hopefully that one was okay.
Yeah, I didn't find that
All
hard,
right. Question 5 on waves. How was this one for the two of you?
Wasn't too bad, I guess. But I need to go over in a little bit.
Yeah. So diffraction of waves for AS level physics, it tends to be one of the most mathsy topics because it involves lots of trig and triangles and all the other weird stuff. So first of all, the diffraction of a wave. What does it mean?
Diffraction of a wave. Isn't it when a wave passes through, like an edge of a wave spreads?
Yeah. So I think one of the best ways of thinking about diffraction is the idea of when a wave passes through a small gap, that gap ends up acting as a kind of source in a lot of ways, right? So I'm just going to borrow this space down here from the next question. So if we have a little gap, we get a wave coming out of it in wavefronts as though there was in fact a source in the middle here that was emitting those wavefronts. Except actually what we've got is a wave coming in. That is diffraction. It's light going through a small gap and then it spreads as though from a new source. Okay, so we have laser light. You will always have laser light when you talk about diffraction at this level. Why is that? What's special about laser light?
I'm not too sure.
Niels?
I actually have no clue why laser light in specific is...
Cool. So, what is special about a laser is the fact that you can say this. So, laser light is light of one wavelength. More specifically, it is coherent light of one wavelength. So it means it's all in sync as well.
Yeah.
Regular light will be made up of lots of different frequencies of light and all in a kind of jumble. Whereas laser light, it's all going at the same, so you've got lots of waves and they're all in the same phase.
Yeah.
And they're all at the same frequency. Whereas regular light might look like, oh, we've got this and then we've got one of these and we've got something like that. And, we've got a whole bunch of different stuff going on. Okay, yeah, no, okay, writing quickly, terrible idea, note to self for future. Cool. Okay, so, I've sort of written Lasker or something there, haven't I? That's bizarre. Okay, so, yeah, that's what's important about laser light. So when you see light of a certain wavelength, it always has to be laser light, because laser light is how you get light of only one wavelength. And the reason that we need just one wavelength is because when you start introducing different wavelengths, they don't interfere with each other properly. And you just sort of get weird stuff going on. Usually they kind of ignore each other, to be honest. So that's why laser light is important here, and that's why we're using it, because it's just one wavelength. All right, so for the diffraction grating, the minimum possible line spacing. So this one is actually a bit of an interesting one.
Yeah, I agree.
So let me... Yeah. Oh, come on, I should be able to... There we go. Let me clear up my page. That'll do. Okay, so this one is quite an interesting one. The key to this question is up here, including the fourth order maximum. So our diffraction equation, let's start with that. We have n lambda equals d sine theta. There we go. N lambda is d sine theta. So d is what we're trying to find. Lambda we know. It's the other two that we're interested in. So when we talk about a fourth order maximum, what does that tell us for this equation? What does fourth order mean? What do we mean when we talk about fourth order?
I don't know. I've not learned that. What fourth order is?
Cool. So this equation below, what does it mean? Explain it to me. Either of you.
So then n would be the order, I believe, if I'm...
Yep.
Yeah.
So what values can n take?
I believe n can take anything from like 1 to a very large number. I'm not... N in general, for pretty much everything, means any integer. Yeah.
That's what it means. Yeah, so n is the order, lambda is the wavelength, and d sine theta, where theta is our angle. So we're saying, okay, we've got our source, and we're coming off, and we're at an angle theta to the straight on.
Yeah.
That's what we're doing. Now, what we're saying here is we have a fourth order maximum.
Mm-hmm.
So we are projecting a fourth order maximum onto some screen over here. All right? So for our fourth order maximum to exist, what condition do we need when n equals 4? What can we say about theta for our fourth order maximum if it exists? This is the kind of the crux of the issue.
The theta can, well, you know, you don't know. Should I answer instead?
Yeah. By all means.
So theta can equal 90 degrees, or sine theta could be just 1.
Okay, so there is a catch here. Not equal necessarily, right?
Okay.
What we're talking about here is we're saying, okay, in this case, sine theta, or rather, sorry, for our fourth order maximum to exist, theta has to be less than, or it has to be up to 90 degrees, right? If theta is more than 90 degrees, then we're pointing off somewhere in this direction. And at that point, you know, how is it ever going to get projected onto a screen? But it doesn't have to be 90 degrees. The reason that we actually end up using 90 degrees is because we're looking for the minimum possible line spacing. Okay? So what we're saying here is, in another sense, you can look at it as d equals n lambda over sine theta.
Yeah.
I'm trying to write too fast, and it's just really not going well for me, is it? Okay, n lambda over sine theta. So the other way of looking at it, from a purely mathematical sense, as opposed to the diagram, is saying we need sine theta to be as big as possible, because we want d to be as small as possible, right? So in this case, we're completely ignoring the diagram. We're saying, okay, I've rearranged my equation to find d, and if I want d to be as small as possible, I need sine theta to be as big as possible. The biggest sine theta can be is 1 for our fourth order maximum. And so what we end up with is our n is 4 and our sine theta is 1 to make it as small as possible. And obviously I'm not going to bother putting the numbers in, but yeah. So that is where that comes from. It is probably the trickiest question that we have come across in this paper, to be honest, because it's quite a stretch to go just from what they've said to working out the answer. It is, however, the sort of thing that you want to get used to in terms of doing, because if you can do questions like this, you are in a really, really good spot. Okay, the light in B, which is our laser light of wavelength 500 nanometers, is now replaced with red light. State and explain whether this is likely to result in the formation of a fifth order diffraction maximum. So this one, oh, this one's interesting. Now, first of all, this requires us to actually know what we mean when we talk about the colors of light. So, red light, and indeed our 500 nanometers. What is the relation between this from either of you?
So, okay. So red light is a greater wavelength, so it becomes larger than 500 nanometers. Cool.
So, at a guess, roughly, what's the wavelength of red light?
Mm-hmm.
What kind of region are we talking?
I'm not sure. I haven't memorized the table by heart.
So how do you know it's bigger than 500?
Because I believe it's around 700 nanometers.
Cool. There we go. So where was the trouble?
I didn't want to be wrong.
I
didn't want to be
cool.
wrong.
So this is actually an important point, right? Particularly in things like tutorials and the way that your school does learning. You know, when you're doing lots of practice papers and you're doing a tutorial, being afraid to be wrong is a terrible idea, right?
Yeah.
Ultimately, from a very, very cynical perspective, all that matters, depending on what way you look at it, either all that matters is that you learn things, or all that matters from a more worldly perspective is that you do well on your exam, right?
Yeah.
This is not your exam, so there is no harm in being wrong. But I, and indeed any of your other tutors, can't really help you if I don't know what you know, okay? But more to the point, the other thing I was going to say was, you know, yeah, I was just asking for a vague region. What I really wanted to make sure was that you knew that it was, you know, a few hundred nanometers type of region, as opposed to like, you know, a millimeter or something. Yeah, so 500 nanometers, you're looking at sort of turquoise. It's kind of on the blue end of green, really. No, it's not. It's kind of just green. Yeah, it's pretty green light. So yeah, we've started with a green laser. We've gone to red. our wavelength has gone up. So we have a longer wavelength, and our fifth order maximum is not going to be formed. So why do we know this? I would say that one of the best ways of doing this is actually once again to rearrange our equation, and this time to write n equals d sine theta over lambda. Okay? What this says is that as our wave, and all we care about here is saying, okay, as our wavelength goes up, our number of, our order of our maximum is going to go down. And so if we look at the outer edge with, sine theta is about 1, theta is about 90, then the order is going to go down, not up. And so we're never going to get more maxima than we already have if we are increasing our wavelength. Does that make sense from the equation?
Yeah.
Basically, we're just saying as lambda goes up, n is going to go down.
Okay.
And obviously 5 is bigger than 4. It's a revolutionary statement, I know, but I'm sure you'll get your head around it. So, yeah, our red light is a longer wavelength, and the fifth order maximum will not be formed. Yeah, I would say probably one of the meanest parts of this is the suggestion that essentially they are kind of wanting you to know where you're sitting for your wavelengths of light, which is a bit harsh. So yeah, red light about 650, 700, blue light probably 400, something like that. Okay, let us move on. We have 15 minutes left, so we're kind of on schedule, to question 6. This is our last question. So, first of all, let me ask, did you have any issues with question 6 particularly?
Not really in particular.
Did you guys do much of question 6? Because I thought I heard you at one point say, did you do up to question 5 or something like that? So
I did parts of it, but I have actually quite a bit of trouble with electronics. So
okay,
up onto the resistive circuits and stuff like that, I'm not great at adding up resistance and figuring out the ratios and stuff like that.
excellent, right. Cool. Well, we will focus on that then for this question. So, define potential difference. That's your voltage. Blah, boring. That's just you know it or you don't. So, okay, here we have a very interesting looking resistor setup. So, R1 and R2 are fixed resistors. R3 is a variable resistor. Switch S is closed. Cool. So it's just a circuit. Calculate the current in the battery when the resistance of R3 is set at 0. At 24. Blah, 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 blah. Cool. So, actually, right. I'm having an idea here. So let me just quickly flick through the rest of this question. So, that's entirely separate. Yeah. Okay. Cool. All right. So, fundamentally, all this is asking you to do is, so when it says calculate the current from the battery, right, what you're using is V equals IR, right?
Yeah.
Or, so in this case, more specifically, I equals V over R.
Yeah.
So really what we need is the resistance of the circuit as a whole. Now, you have said to me that you have a little bit of trouble with the way you set up resistance. It's the resistance calculations. And fundamentally, this whole question is easy, provided you can work that out. So if it's all right, actually, I think what I'm going to do is I'm going to spend the last 10 minutes just going over with you resistance calculations rather than this question specifically. Does that seem okay? Is that okay with both of you?
Yeah.
Right. Okay. So there are 2 points. Number one, there are two types of resistances, of resistance additions. There are, number one, series. Series is really very nice and easy. Okay? When resistors are in series, you add them up. It's that simple. I'm sure that you are very comfortable with that part of things.
Yeah.
The trickier part is when they are in parallel. And when they are in parallel, you have essentially, it's just I would just think of it as the equation for resistances in parallel. And it looks like 1 over RT, if only I could draw, 1 over RT equals 1 over R1 plus 1 over R2 plus ... Okay, I can't draw 3 dots because this doesn't really like picking up dots, but that's life. So this is your equation, right? It's 1 over your total resistance is 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3 plus blah, 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 for as many resistors as you have in parallel. Okay? This is in itself, it's a slightly nasty equation because once you actually want RT itself, you end up with 1 over a sum of 1 overs, which just looks a bit weird. But fundamentally, as long as you have numbers to put into them, it's all right. Okay? One of the biggest issues that people often have is deciding whether things are, like, what order to do things in, essentially. So we're going to use this question as an example. So first of all, tell me about the setup. What is in parallel with what? Either of you.
R2 and R3.
Yeah. R2 and R3.
Yeah, R2 R3.
Cool. So R2 and R3 are in parallel with each other. What is in series with what?
So R1 and then the parallel of R2 and R3 are in series.
Yeah. I agree.
Yeah. So R1 is in series with the combination. And functionally, that is what you do, right? So when you have resistors, the way you do it is you do it from the smallest building blocks first. So you go down to find the smallest level building blocks and you build your way up out from there. So the way you would do this is first, you would take your building block of, you would take your bits that are in parallel and you build that up from that level. So, you know, your other building block is just R1. I mean, you already know the resistance of that, so that one's kind of boring. So you zone in, and then you take the smallest ones first. So in this case, we can say, okay, our resistance of this combination is going to be 1 over R2 plus 1 over R3. And then we're going to combine that with R1 as a series calculation. Now, if, for example, you had another resistor, R4 by here, which I'm going to imagine for the sake of this, right?
Yeah.
Then what you would do is you would say, okay, we have R4 and R2 are in series with each other. That combination is in parallel with R3. And then that overall combination is in series with R1. Does that make sense?
Yeah.
Okay. In that case, what you would do is you would say, okay, first of all, we have this kind of combination by here. And the total resistance of that is R2 plus R4. Then we would do the resistance of the parallel combination, which would be 1 over R2 plus R4 plus 1 over R3. And then finally, we would add R1 to that. Does that make sense as to the order that I've done those steps in?
Yeah.
Yeah. So you may be wondering, the reason that I have added this mysterious R4 in when it wasn't there is because once you get to that level where you've got a series within a parallel within a series, that is essentially as complicated as it's going to get at this level, right? Because any more than that, and it's just kind of weirdly superfluous. They are unlikely to do a sort of parallel within a parallel type of thing to you. Other point. If I had, 1, 2, and 3 here, what's in parallel with what? What would be your combination to find the total resistance of if they were R1, R2, and R3, like I've drawn them there?
So the combination would just be 1 over RT equals 1 over R1. Or did I miss?
Sorry. I'm talking about this one over here. So I've just written 1, 2, and 3 rather than R1, R2, R3.
Yeah.
So in this case, what would be 1 over RT? It would be 1 over R1 plus 1 over R2 plus 1 over R3.
Yeah.
Yeah? Yeah, okay. I just wanted to make sure because sometimes people get themselves confused, and what they try and do is they try and do sort of this bit and then do that bit in parallel with the other bit.
Oh.
That's actually not wrong. It's interesting because if you actually do the algebra of it, you actually come out with the exact same thing. That is where this kind of 1 over 1 over 1 over thing comes from, is the fact that they are all blocks in parallel, but you don't need to, and it makes your life easier. So yeah, that is kind of resistors in a nutshell. What you want to do is you want to look from the biggest level first, so with the 2 big circled areas on our diagram, and then you keep breaking them down until you find something that you can just do, and then you work your way back up from there to the highest level. Does that make sense as a way of kind of approaching these?
Yeah.
Okay, so.
So yeah, I mean, resistors are one of, particularly, the whole parallel and series thing, it is one of the trickier things with the sort of A-level maths of circuits type of stuff. I think that's the best way to approach it, is just continually breaking things down into little chunks and then working out the relationship between each chunk. And don't be afraid to just do each chunk one at a time and then put the answer in. I would advise against trying to build, giant block equations like this, because they just end up looking really messy. So I would advise doing it step by step and actually taking the numbers through. It is one of the very few things where I think that is probably the better idea at this level. So yeah. All right. So, and yeah, that kind of follows through for the rest of it. For part 2, it's the total power. Well, again, that's just writing with my mouse for no reason. P equals I squared R.
Yeah.
That one's fine. And then the last one is a little odd, but this is I equals nave. Yep. And if you rearrange that, you get V equals I over N A E. Now, in this case, when we do that ratio, well, obviously E is the same because E is just the charge of an electron. But because they are, we've said the switch is open, when the switch is open, you lose resistor 3 completely, right? It's no longer part of the circuit. And so they're just in series at that point. If they're in series, they have the same current. So we don't care what the current is, we just know it's the same. So when we do V1 over V2, we get N2 A2 over N1 A1. And we've been given these values, so yeah. Or more specifically, actually, we've been given this value and this value. Does that make sense?
Yeah.
Cool. That is the whole of the paper. I think, and that brings us to 5 o'clock exactly. So I think that is probably a good place to leave it. Are there any further questions that you would like to ask before we disperse for today?
I'm happy with what we did.
Yeah, same actually.
Good. All right. In that case, I think I will be seeing you, presumably it's you that I will be seeing on Thursday. And I hope you guys enjoy your trip tomorrow.
Yeah, thank you.
Conrad, thanks very much for that. Fantastic.
Excellent. Right. Cool.
Conrad, we've just got to kick off the next ones now, but we'll catch up on WhatsApp and appreciate any feedback that you've got. We'll have a look at it. Okay, buddy. Speak soon.
All right. Thank you very much. Bye-bye.
Bye.
No, don't do that. We still have to met ourselves.